Welcome everyone to the 98th meeting of Directions in Group Theory and Triangulated Categories. Today our speaker is Marc Stephan from Bielefeld University, and he'll be talking to us about an equivariant BGG correspondence and applications to free A4 actions on products of spheres.
Thank you for having me in this seminar series about group theory and triangulated categories. We'll be interested in finite groups and in particular their actions on finite CW complexes or in particular spheres and products of spheres. But also triangulated categories will appear because we will need a certain equivalence of triangulated categories, and this will be this equivariant BGG correspondence. And the group we are mainly interested in is the group A4, the alternating group on 4 letters. And as a teaser, I would like to start with the following questions. So let's look at perfect complexes over the group ring of A4 with 2 coefficients. So perfect means that they are bounded and consist of finitely generated projective modules. And let's insert a condition, namely I want that the total homology is 4-dimensional. So the sum of the petty numbers is 4. And maybe why is this an interesting condition? It turns out that if such a perfect complex has non-zero homology, then it is at least 4-dimensional. So these are the ones with sort of minimal homology. And let's insert more condition, namely that we should not only be 4-dimensional, but we also want to fix where this homology should lie. So let's say we have 4 homogeneous basis elements and they lie in the following degrees. Let's say the smallest degree should be in degree 0. Then we have 1 in degree 21, 1 in 37. And the last one is some number k that should be bigger, but we don't fix it. I don't know if anybody has an intuition what the answer will be. So if anybody wants to say something, please do. I don't think it will be obvious. So the answer is 0. But if we change the third degree a little bit, let's say we use again 21, but then we want to have homology in degree 35, and in some case, then it turns out that there are perfect cochain complexes. And when I say we want to count them, I mean actually up to quasi-isomorphism, which is the same as chain homotopy equivalence because they're perfect. So then we do have some perfect complexes when k is the sum of the 2 middle numbers, 21 plus 35, so 56. But otherwise, we don't have any. And I don't know if anybody wants to guess how many there could be. Just mention a number. We have some 27, 14, thanks a lot. So the answer is 9,831. All right. And so this is a bit the teaser for this talk. And now I would like to explain in what kind of perfect complexes are we interested in and why are we interested in these perfect complexes. And the interest comes from topology. Namely, if a finite group G acts freely on a finite CW complex, and here I usually mean that we actually have a GCW complex structure. So the action takes cells to cells. So because it's free, this is the only condition.
Please keep asking us these questions. It's fun.
All right, thanks. So if we have such a finite CW complex with a free G action, and then we look at its cellular chain complex or cellular cochain complex, then we get perfect complexes. Let's look at a very basic example. Let's look at the circle S1 with the antipodal action. So by the cyclic group of order 2, and I'll call it generated tau. Then we have the following CW structure. We have 2 points, x, and then the tau of x. We have 2 one cells. That would be A and tau of A. We can write down its cellular chain complex. We have 2 coefficients. So in degree 0, we have 2 times the vector space, 1 with basis x, and then with 2 times f, 2 ones with basis tau x, and in degree 1 we have the same but with A. And then we have zeros. And so in both cases, this is just a group ring. And what does the boundary do? Okay, we take endpoint minus start point, so we have to multiply with tau minus 1. Okay, and so we get a perfect complex. Now, for our example where we work over A4 and we wanted to have 4-dimensional homology, and this should be concentrated in these degrees 0, 21, 35, and 56, we got like 9,831 31 perfect complexes. Now we can ask how many of these are realizable by a finite CW complex with a free A4 action. Does anybody have a guess what's the answer there? So for any of these, for how many of these can we find a finite CW complex with a free A4 action such that the cellular chain complex is the perfect complex? And since Henrik knows our work very well, 42 is always the best answer. But Henrik cheated because he knows our work, and so he knows that the answer is that none of these can be realized topologically. All right. So this sort of completes the teaser. Are there questions? All right, then continue.
I have a very silly question. So regarding this last question that you asked, the answer to which is none. So I'm guessing this none answer depends very crucially on A4, right?
Yes, everything I do depends a lot on A4. I don't know answers for other groups. A lot will be quite specific about A4. Yeah.
Okay,
I mean, of course, one can ask similar questions for other groups. It's not so clear if one would get such precise answers. Yeah. All right. So let's continue a bit more with topological motivation. Namely, comes from rank conjectures. And a classical problem is to ask which finite group can act on a sphere, on a product of spheres, or on a finite CW complex act freely. And okay, I want to exclude the trivial group because, I mean, this always acts freely. For instance, if we look at a sphere of even dimension, then the only finite group that can act freely is the cyclic group of order 2. And this has a very easy justification, namely the order of the group has to divide the Euler characteristic. So if X is homotopy equivalent to a two-dimensional sphere, then we only have the cyclic group of order 2. And an early result that also includes odd-dimensional spheres is by Smith, that states that if G acts freely on Sn for some n, then it cannot contain a subgroup of the form Cp cross Cp's for any prime p. So an elementary abelian p group of rank 2. And Benson and John Carlson conjectured in the 80s that if we want to look at products of spheres, so let's say we want to have R spheres, and we ask, can a finite group G act freely on a product of R spheres or on a finite CW complex of this homotopy type, then this is only possible if the rank of G is at most R. And maybe not everybody knows what the rank is. So this is the maximal P rank, where P is a prime. i.e. The maximal K such that C mod P to the K embeds as a subgroup into G. And at this point, the conjecture was already known in the case of rank 1. This is by the result of by Smith together with work of Swan. For the other direction. And when the rank is 2, then we know that the conjecture holds for P groups. By work of Alejandro Adam and Jeff Smith from this century. But it is already open for simple groups of rank 2. Now, if you look into the classification of the simple groups of rank 2, you learn that every such group contains A4 as a subgroup. And this is one motivation to look into A4. And there are some non-existence results for dimensions where we cannot have a free A4 action. So free A4 action on a finite CW complex X of the homotopy type of Sn cross Sn. Namely, Bob Oliver showed that we cannot have a free action when the dimensions are the same. And then Plaschik in 2013 gave sort of an overview of what is known and also proved that we cannot have a free A4 action on S1 cross Sn. So when n is 1, we also don't have a free action. And lastly, again, easy condition is that not both m and n can be even, again, because of Euler characteristic. So again, because the order of A4 must divide the Euler characteristic. So now we one can ask like, okay, how many pairs can have an action? How many pairs cannot? Like sort of both seem to be infinite. So it's a bit hard to say how to compare them. But if you make like a table where you have like n in one direction and m in the other direction, then, and let's say the n should be the bigger number. So we exclude the diagonal and we exclude like the smaller number 1. And then we only look at things in this triangle. And then we have also this condition about not both even. So if we have an even, then that's not in there, then we can have something. Then again, something not. We have odd, even. It would look like this. Where we could have something. So where I'm going there is sort of, if we fix somehow the size of these triangles and let them become bigger and bigger, then we just sort of exclude 1/4 of the points. So let me write this down. So if we fix R in n, and then we consider the existence of 3 A4 actions on Sn cross Sm, then at most 3/4 of these pairs Nm we can have such a free action. So for at most 3/4 of the pairs, where m and n are smaller than r. And what we're going to show is that the percentage of the pairs where one can have a free A4 action actually goes to 0 when this R goes to infinity. So we'll provide much more obstructions. Are there further questions? Okay. So I said that we'll look at the questions very algebraically. So let's start with thinking about perfect complexes. And for that, it would be helpful to think of the group A4 as a semi-direct product, where the cyclic group of order 3 acts non-trivially on C2 cross C2. And to state our result, we will need some actions. And for that, we consider a field F, any finite group G with normal subgroup P, but G will play the role, or A4 will play the role of G, and C2 cross C2 will play the role of P. And so we get a short exact sequence of finite groups, 1 to P to G, and then we take the quotient that I'll call Q. So this is our Q. And we consider to write Fg modulus M and N, and we can look at the Fp module homomorphisms from M to N. And on this, we get a right Q action where on a homomorphism, an element Q acts if we plug in some element X. So this Q will have a representative G. And we act by f of x G inverse G. And if we extend this to Hom complexes, in particular, if we take a projective resolution of our field over Fg, and we take any cochain complex of right Fg modulus, then we get also with this formula right Q action on the Hom complex. And if we take the homology of this Hom complex, we get X Fp from F to C. And we get also Q action on this like hypercohomology. And one additional fact is that if we look at the action given by composition of X groups, so we look at X Fp star Fc answered with F or F of X Fp Ff. Then from composition, we get this action map to X or Fp from F to C. And on the left-hand side, we can take the diagonal Q action. We have a Q action on the right-hand side. So this is a map Q modules. And so here, let me also use the notation for group cohomology. That's H star of P with coefficients in F. We can look at the annihilator ideal of this action. I will call it JC. C refers to the cochain complex C. So the annihilator with respect to the group cohomology of this module. So this will be now a Q invariant ideal. So closed under the Q action. And now in the specific case, where our field is of characteristic 2, or actually, I mean, here I'll write F2, it makes it a bit simpler. And our P is C2 cross C2, sitting inside some group G such that the quotient is of odd order. Then we get a classification of perfect complexes with four-dimensional homology, namely the assignment where we look at a perfect complex of four-dimensional homology. Everything up to quasi-iso. And these are classified by some integer and then a Q invariant parameter ideal in the group cohomology. So in this case, so P was C2 cross C2, so the group cohomology is just a polynomial ring in two variables of degree 1. And so what does it mean in this specific case to be a parameter ideal? It must be generated by two elements, homogeneous of degree at least 1. and we want that the quotient is finite dimensional as a vector space. All right, and the assignment is given by, we take the perfect complex and we look at its minimal degree where it has non-zero homology, minimal L such that HL of C is non-zero. And the ideal is exactly this annihilator ideal that we defined before. So the statement is that this is a bijection. Moreover, so this L, I mean, basically just tells you we can shift the perfect complex up and down, but let's say the lowest is now in degree 0. So if H star of C has basis elements in degrees 0, M, N, and K, then this last one must be the sum of N and M. And the parameters of degrees n plus 1 and n plus 1. So one higher than where we have the homology. Now, in order to prove this result, we have a spectral sequence argument where we filter the cochain complex by powers of the augmentation ideal of the group ring for P. And then because we have this assumption that the homology is four-dimensional, it turns out that the spectral sequence collapses on the E2 page. And then with some help of commutative algebra, you'll get that this annihilator ideal must be a parameter ideal. So I will not say much more about this. On the other hand, to get the bijection and also the way we construct the perfect complexes from the parameter ideas is not directly that we work with chain complexes over the group rings, but we'll actually work over the group cohomology with DG modules. And for that, we need an equivariant BGG correspondence. So this is the second ingredient. And so the next step will be to talk a bit more about this equivariant BGG correspondence. Are there questions about this classification of perfect complexes, a four-dimensional homology? All right. So the group ring for an elementary abelian 2 group over a field of characteristic 2 as an exterior algebra. And this is what we'll consider in the equivariant BGG correspondence. So usually the Bernstein-Gelfand correspondence is equivalence between two triangulated categories. On the one hand, you have graded modules over an exterior algebra where generators are like in degree -1. On the other hand, you have a bounded derived category of graded modules over a polynomial ring with generators in degree 1. But we'll use a different one, which is due to Gunnar-Carlson, where we don't work with graded modules, but instead we work with DG modules. So how does this work? We fix a finite dimensional vector space V of over a field of characteristic 2. We look at the exterior algebra. We don't grade it, or if you want to look at it as a like BGG algebra, you can put it in degree 0. And then we take the symmetric algebra on the dual vector space, but this will have a grading, namely the dual vector space is in degree 1. And we consider this as a BGG algebra with 0 differential. Then what Gunnar Carlsen showed is that if we look at the derived category of perfect complexes over the exterior algebra, then this one is equivalent to some derived category of DG modules over S. And what's the meaning of this HF? So this HF stands for homologically finite. So we look at DG modules over S such that the dimension, so let's say F is our field, such a dimension over F is finite. And I wrote here S perfect, so it should be lying in the fixed subcategory generated by S inside all the derived category of all DG modules. Or equivalently, this DG module has to be quasi-isomorphic to a DG module where the underlying graded module is finitely generated and free over S. And I've also written that there is an extension of this result, namely this is a restriction of a equivalence of triangulated categories on bigger categories, which is not stated exactly like that in this paper of Avramov, Buchweiz, Iyengar, Miller, but with the same methods it can be proved. I mean, they also work with DG modules, but they have a bit different gradings. And namely, these sit inside, on the one hand, we can take here all S-perfect DG modules, and on the other hand, we can take the bounded derived category of finitely generated lambda modules. And we have equivalence of triangulated categories also on this bigger one. Now, if you want to extend this equivariantly, we can take a finite group Q and suppose it acts on V, and so it will also act on the exterior algebra, on the symmetric algebra, and the result extends as follows. So the reason I wrote all these perfect subscripts and not already in the category somewhere is that now it extends easily. So we can now just take the skew group algebras for lambda and S and add them here. And this will give us the equivariant version. So note that we still just ask that the underlying DG modules over S are perfect. And here also that only the underlying DG chain complexes over lambda are perfect. All right. Are there further questions? Then I'll continue with the parameter ideas. So now in our case of interest, where we look at the alternating group A4, we think of it as a semi-direct product of C3.
Mark, I had a question. Can you just go up to these equivalences? So the equivalence between like the first horizontal one, is that equivalence an if and only if with the lower equivalence?
So it is true that, I mean, the upper one restricts to the lower one. I think, I mean, you have to calculate somehow where like generators are sent to, like of like 6 subcategories. So here you basically check that the S gets sent to the field.
Right. Yeah. Okay, thank you.
Okay, thank you. So I'd like to go back to our motivating question or the teasers in the beginning. So for that, we want to consider now A4. And if I said already that the group homology is a polynomial ring in 2 generators of degree 1. And let's say phi is a generator of C3, then if we do somehow consistent choices, then the action of this group on the group homology sends one generator to the other one and the second one to the sum A plus B. And now if you want to classify perfect complexes, let's say that have to have homology in degree 0, n, m, and n plus m, then we need to look at n plus 1. This should be this n prime. At n plus 1, this should be this m prime, and compute the C3 invariant parameter ideals with parameters of these degrees. And this can be done, but I don't want to now write many formulas. Maybe let's just look at one formula. So in case where n prime is bigger than n prime, so in general, this depends on what m prime mod 3 and n prime mod 3 is. So in case m prime is 1 mod 3 and n prime is 0 mod 3, then it turns out we get 3 to the 3 or 5 times 4 to the I minus 1 to the I such C3 invariant parameter ideas. So in particular, this doesn't depend on the J. And let's think that this actually makes sense. So 4 is the same as minus 1 mod 5. So we can actually divide. So we haven't made a mistake there yet. And in particular, if we look at the question from the beginning, where we were interested in somehow degree 21, so the parameter is 1 bigger, so we need to look at 22, which is 3 times 7 plus 1, and then the other one was like 35, so we look at 35 plus 1, 36, which is 3 times 12. Then we obtain 305 times 4 to the 7 plus 1. And if one plugs it into a calculator, one gets this 9,831 from the beginning. Okay. Then we can ask the additional question, is such a perfect complex realizable? So meaning, does there exist a finite CW complex X with 4-dimensional homology? Oh, no, sorry. X such that its chain complex is homotopy equivalent to this perfect complex. And so if you want your perfect complex to come from a finite free CW complex, with the free A4 action, then you have more properties for this annihilator ideal. Namely, it has to be closed under Steenrod operations. And in particular, if you take all these Steenrod operations together, you get a ring homomorphism, which is the total Steenrod operation. And in the case of the group ring for C2 cross C2, it sends A to A plus A squared, and it sends B to B plus B squared. So you have more restrictions if your perfect complex has to come from a space. And now with Henrik and Ergün, we have classified all these Steenrod closed C3 invariant parameter ideals. Instead of writing down all the lists, let me just mention that we have this classification. So this was in the group cohomology of C2 cross C2. And what comes out of the classification, which I found surprising, that if we fix any degrees for the parameters, there is at most one such ideal with parameters of these degrees. And this has strong topological implications. Namely, if A4 acts freely on a finite CW complex, the homotopy type of a product of two spheres Sn cross Sm, then a cellular cochain complex up to quasi-isomorphism is determined just by the degrees. And also the homology of the quotient. So since we have a free action, this is the Borel homology, which usually should tell you something about the action, is also only determined by the degrees. And actually, it's not really important that it's a product of spheres. All we need is that the cohomology lies in degrees 0, n, m, and n plus m. So if you tell me now, okay, I've constructed this free A4 action on, I don't know, S200 cross S311, then I will already be able to tell you what the cohomology of the quotient space is. So it will be the cohomology of the A4 modulo the intersection of this ideal for this cochain complex with the cohomology of A4, where we think of the cohomology of A4 as the C3 fixed points of the cohomology of C2 cross C2. Okay. And let's have an overview maybe on where can we have which degrees can appear as parameters. So this looks as follows. So here I'm only looking at parameters where the n prime is bigger than the m prime. And in the beginning, we had this question, oh, is any of these 9,831s realizable? So we need to look at parameters of degrees 22 and 36. Let's go into the table. Do we have a parameter in degrees 36 and 22? We don't. So the blue points, they tell us where we have a parameter ideal with the corresponding degrees that are written up here and here. Now, we can also think of, okay, now how many pairs would now still be realizable? And before we saw like, oh, there will be at most 3/4 of the pairs that are realizable. But now if we like take bigger and bigger boxes, we see somehow that the ratio of the ones that are possibly realizable versus the ones that are not realizable becomes smaller and smaller. And in fact, we can show that it tends to 0. So that's the last consequence. The percentage of the pairs and in them which are at most R, such that A4 acts freely on a finite CW complex homotopy equivalent to Sn cross Sm tends to 0 as R goes to infinity. Then let's finish with a question, namely, we would be very interested to know if there is a free A4 action on S10 cross 11. So this is the first pair we don't know. And what we do know is that the cohomology of the quotient space would be as follows. Would be the cohomology of A4 where we divide out some parameter ideal, and this is generated by some V that I'll describe shortly, times U to the 4 and V to the 4 plus U to the 6, where V is AB times A plus B. It's an element of degree 3, and U is a squared plus ab plus b squared. So we have no idea if there exists a free A4 action on S10 cross S11. We don't know either if there is a space that has this homology ring. All right. So I hope I managed to explain why for certain degrees of perfect complexes over A4 with four-dimensional total homology, they exist. When they exist, why we know how many there exist, and what kind of restrictions we get for topological realizability. So this would be the end, and I'm happy to answer questions.
Thank you, Mark. Yeah, let's all unmute ourselves and give the speaker a round of applause now. Okay. Any questions, anyone? Wasn't there a big theorem by Alejandro Adem and the Adem-Smith theorem about like free group actions on these kinds of things? That I think you mentioned it, right? At some point.
Yes, this is what I mentioned, that they proved like the rank conjecture of Benson and Carlson for finite P groups of rank 2. So they have, so in the case like rank 2, we know that this condition is necessary, but it's not known if it's sufficient. So they have homotopical methods to construct free actions.
Right.
But it's not clear. Yeah, it's not clear how you would do that for all the simple groups of rank 2, for instance. In particular, there's this group that people don't know, which is called QDP, which is a semi-direct product of CP cross CP with SL2P.
Right. I'm trying to find this paper. So there was a paper. So, I mean, of course, this story doesn't quite carry over into infinite groups, but there was one paper by, I think, Guido Mislin and Olympia Teleli from the turn of the century, where there was basically a connection between the existence of such an action and, I think, periodic homology.
Yeah. I mean,
Trying to find that result. Just a second. Yeah, and that stuff was, I mean, this thing was for infinite groups with some finiteness conditions, with some finiteness properties assumed of it. Yeah, I can't seem to find it just yet. I mean, I know which paper it is. It's called On Groups Which Act Freely and Properly on Finite Dimensional Homotopy Spheres.
Thanks.
I can't find the exact result that I'm. I think it's theorem B of this paper. But anyway, right. Any more questions? So there's also a generalized. I think Peter Berg was giving a talk on this thing in Greece last year. So this Benson-Carlson rank conjecture that you have on the screen right here, wasn't there a generalized version of this conjecture afterwards by somebody else?
Maybe you mean like the conjecture of Garner-Carlson about free actions of elementary abelian P groups, that if you have a free action of an elementary abelian P group of rank R on a finite CW complex, then the sum of the mod P Betti numbers must be at least 2 to the R. And then you can think about this also just for perfect complexes, and And when P is odd, there are counterexamples by Mark Walker and Shrikant Iyengar,
Oh,
which
yeah.
Henrik and I proved to be non-realizable. And probably you mean the work of Peter Berg, which has somehow extensions of these to other settings.
Yeah, right. I want to say there was an extension to, no, not tensor categories. Like, yeah, maybe I'm thinking about that.
Yeah.
Thanks for reading my mind.
Yeah.
Yeah, you didn't mention that conjecture or that line of work in this talk, right?
No, I did not. Okay. But it's related.
Mm-hmm. Now, I remember you and Henrik being mentioned in Peter's talk, and I didn't realize at the time that Stefan was you. And afterwards, Janina told me that this is our Mark. Okay. Any more questions? Anybody else?
Just want to make a remark on this Adam Smith results. It's not for finite groups. There's infinite groups also involved. Just a definition of periodic group, and then the theorem says under this definition, a group is periodic if and only if it has a fibration over its classifying space with five pairs.
Right.
It involves the infinite groups as well.
Right. Yeah, that's the one.
Nice, very nice. More general theorem. The second remark is simple groups of rank 2. There's only one missing, PSL 3FP.
Nice. Okay.
It's open only for one of the simple groups. And also for finite groups, I think it's true if QDP is not involved. Like there's a statement that except certain type of finite groups, it's always possible to find this action for rank 2 finite groups. So there is stronger results that in Adam Smith paper if you want to dig through it.
Yeah,
it's a nice paper.
Yeah, I remember when periodic cohomology. I mean, yeah, there was as you said more precisely. As you said more precisely just now. Yeah, there was a connection. Yeah. Okay. I mean, I remember using some things from that paper, but only those things. I didn't know what the rest of the paper was doing in relation to complete resolutions and complete cohomology in my PhD. That's why I sort of half remembered it. Any more comments or questions, anyone? Okay, in that case, let's thank Marc once again. It's the 98th meeting, and I'm sorry, Marc, I should have really called you, asked you earlier to give a talk. I don't know how it slipped my mind.
Oh, no, thanks for having me.
Yeah.